Thank you, everyone. Hello and welcome, and thanks, Alan, for that session beforehand, and for keeping on time as well. That's quite a challenge after our sing-song, I think, earlier. The other thing that was interesting, actually, about the last presentation is metadata. If I was here maybe last year, I might have been talking about metadata. I worked on a project called Egeria. But now's this year, and it's a different project and a different topic, so we'll start. So I'm here with my colleague, Alex. He's going to be speaking a little bit later in the presentation. We both work for IBM. We work within the quantum organization in IBM Research, and we're both software engineers. So we are not quantum physicists and mathematicians. So if you have any difficult questions about quantum, tell us the answers, and that would be really helpful. So what we're here to talk to you about today is one of the challenges that we've got with cryptography. We're going to take you through what is cryptography, a quick summary. I think many of you will know that. A little bit about what is quantum computing. Remember, no hard questions. One of the threats that we see today from quantum computing, and then what are some of the things that we can do about it. And really, that's the key thing that we're all here about, is to try and learn about these things and figure out what does that mean about what we do in the future? How do we actually make things better? And how can we collaborate and do it between us? We might even mention S-bombs or C-bombs and something like that later. So the first thing to think about is, what is cryptography? And at its essence, really, all it is about trying to keep things secret. So we want to be able to exchange messages with people without other people knowing about them. But if we look into it, there's a little bit more detail behind that. There's some characteristics of cryptography that these solutions offer us. One of those, authenticity, is about knowing where did that message come from? Who was the actual originator of that message? So what is that source? Once we know that source, confidentiality is about saying we don't want anyone else to be able to see it. That's the real secret bit. It's only visible to those people that should be able to see it. Tampering is a problem as well. If you send a message from one place to another, do you know it's the same as it was where we started? And actually, if we look at things like supply chain, of course, and we're looking at hash codes, etc., of software packages, we want to make sure that isn't tampered with. So integrity is all about making sure it's not tampered with. And finally, another challenge we have is wanting to make sure that if someone says they've sent you something or they're doing something as part of a contract, they can't take that back. They can't say, well, actually, we didn't send that message. So non-repudiation is an important characteristic too. And of course, all of our business that we do these days depends on those characteristics to make our business, our personal lives work. A quick summary on some of the different types of cryptography. Hashing is where we basically build a digest, a short piece of information from that long text that we're dealing with. And we can use that to make sure that what we've got is what we thought we had. So the data integrity, try and help make sure that that message has not been changed along the way. And there's some characteristics about that we can't reverse engineer the text that we try to send from those hash codes or those digests. And also that we know it's unique. So we're not going to get two different pieces of text that generate the same hash code. So that's cryptographic hashing. Then we have symmetric encryption. That gives us confidentiality because we've got a key that we encode that message with. No one else can see it. But it's very much a one-to-one thing. So we both have to share that key. And when you actually want to try and then scale that up to exchanging messages with lots of different people, that gets difficult. How do you actually manage these keys? And if you go back and look at Diffie, who was one of the founders of the Diffie-Hellman algorithm, I think he was working with telcos at the time, and they were thinking, how can we exchange messages with all these people in the phone book? Because we can't all have different pairs of symmetric keys that we share. And that's actually what led to the development of asymmetric encryption, which is what we use today, often to generate then symmetric keys that we use later. So for example, in a TLS session, we're encrypting traffic. The first stage is to establish what that secret is that we use to then encrypt the rest of the data. That's often known as public key encryption. So we have a public key that everyone can see, and they can use that to for example, send a message or to verify signatures so that we know what we've got. RSA, DSA, two of the common algorithms, they've been very successful. In fact, a lot of the issues with cryptography often end up to being implementation attacks or side channel attacks, or humans, of course. We're often the weak link in the chain. So very successful. There have been some mathematical improvements in terms of the use of elliptic curves, which have improved the security of some of those algorithms. And so we've done pretty well today. But this is really the key thing to remember, that cryptography is all about depending on hard maths problems. So our computers today find it difficult to do these kind of reverse operations. So we would have a maths operation that is simple to do in one direction and is difficult to do in another direction. And that's really what cryptography depends on. Okay, quantum computing. Now, this is wacky. I did part of my degree in physics. I think it's a fascinating area. I loved quantum physics. And so, those principles have been known for a long time, since the beginning of the last century. And quantum computers are making use of some of those properties of quantum physics to help with the way we do these calculations. So what do we actually have with quantum computers? Well, with normal computers, we have bits. We have their, 0, 1. Quantum computers aren't really like that. They've got these things called qubits. And qubits have effectively a superposition of different states. And one of the things that allows us to do is basically a lot of parallelism in terms of how these calculations happen. Another principle that we see in quantum computing is that of entanglement. So that is that two different qubits can be related by the operations that you've done on them, and then we can take them apart, and when we actually look at the value of one, we can tell what the value of the other is. It's very weird stuff. We can talk about quantum transportation, all kinds of things like that. With the quantum computers that we have today, we build these things called quantum circuits. These are gates, and if you think about classical electronics where we have AND gates and OR gates and NOT gates, it's the same kind of thing, but they're operating on these qubits. So it's a very, very different way of working. So what are the things that we can do with quantum computers that we find difficult today? Well, the first one actually is all about materials. It's all about understanding how real atomic bonds, for example, work. We can model that very effectively on quantum computers. That helps with areas like drug discovery, material science. I was listening to a talk the other day. I think they were talking about carbon capture and look at what materials are really good for carbon capture. Also in the finance space, in terms of modeling, optimization problems, climate change, all of those areas where there are complicated calculations to do, and we're starting to look at some of these quantum algorithms that can do these in a more effective way. So coming back to cryptography, what do we have in terms of the threat here? Well, if we look at something like RSA or some of the classic algorithms we have for public key encryption, they're based on certain mathematical problems, such as the factorization or prime factorization. So we have a very big number here. What two numbers do we multiply together to get that big number? One of those may be small, one of those may be big. If we can crack that, we can fundamentally crack that encryption. But we know that's a really difficult problem in normal computing. So there are algorithms that are out there that will help you do this, but for these large numbers, it's going to take a long time. I don't know whether it's millions. I got this slide from somewhere else. It could be hundreds of thousands. Computers that get better. There's some discussion around these classical algorithms. Bottom line is, it's a really, really long time. But what we see when we look at quantum computers is that some of these calculations actually could be done quicker, and we'll come back to that in a moment. And this applies not just to, the initial algorithms, but also to what we're doing with elliptic curves. And one of the most common algorithms that you may hear about is something called Shor's algorithm. Peter Shor was a mathematician who put together a really common algorithm called Shor's algorithm about 30 years ago. And that's kind of, I guess, made us all wake up and think, what do we do about cryptography? Because this is what happens. As the, well, basically with the red line here, you see that's how the classical algorithm scales. So this is doing normal computing, whereas the blue line is what happens when you do it using a quantum algorithm. You can see the blue line's fairly flat, the red line goes up, blue's a lot quicker, the scaling factor is more on a polynomial basis rather than, if you like, exponential. So this is a summary of the two algorithms that you might hear a lot about, and we won't go into too much detail on these algorithms. Shor's algorithm, which can work out prime factors, is what you would use for something like RSA, and it's based on some specific quantum properties around a Fourier transform. If you think of a Fourier transform in the analog space, then this algorithm uses that mechanism, if you like, to help find repeating patterns, which is what it's very good at. There's another one called Grover's algorithm, and this is about speeding up linear search. So linear search through a database, we can do that a lot quicker. It's not the same kind of scaling factor as Shor's, but this actually affects things like hashing algorithms. What we can effectively do there is when we double the key size, we tend to take account of it. So something like Shor is really the one we're most worried about with public key encryption. But the other important point is that these algorithms are still being developed. People are coming up with improvements to them regularly. I was actually listening to a talk by Peter Shaw a couple of months ago, and literally in that talk, there were some PhD students starting to talk to him about the improvements they'd made in other improvements that had been based on top of his algorithm. And these are just two. The important thing to remember, though, is that our quantum computers today are not very powerful. They have, the IBM largest one at the moment, I'm from IBM, has just over 1,000 qubits. That is nowhere near enough to, for example, crack the current versions of RSA that we have. Those also are noisy. One of the problems with quantum computers is you have a lot of noise in terms of looking at the values. And it's something that all of the companies that work in quantum are trying to improve. Improve the number of bits, reduce the amount of noise. And as we do that, we'll get closer to be able to run some of these algorithms. But the estimate in terms of what you might need for Shor today is probably in the order of 10 million in terms of the current qubits that we have. You can see that coming down. NIST, the American organization, reckons perhaps 2030-ish might be where we have quantum computers that are able to crack the encryption that we use today, certainly in terms of public key cryptography. So the question is, what do we do? And also, why do we need to do it? And actually, I should point out this on the last foil, since that's the name of the talk, which is we can basically capture data now and we can decrypt it later. So if you look at some of the bad actors out there, they can harvest all your data now. They can intercept your communications now. They can get that data that's at rest now. They might not be able to decrypt it, but they can save it. They can put it somewhere. Later on, when they have access to powerful quantum computers, they can decrypt it. So a lot depends on what is the value of that data. If it's something that's very short-lived, not very important, maybe like, what's my current location? Do I care if someone finds that out in 5 years' time? No. But if it's health data, if it's financial data, trade secrets, government information, that kind of high-value data, that actually could matter a lot. And some people will say, what about information that's out there now? That's actually a bit too late, so we can't do anything about that. But there are some things that we can do. And so there's been development on what we call quantum-safe cryptography. Some people also call it quantum-resistant. Another term that's used is post-quantum. Different companies have gone their own way for naming. It's all the same thing. And it's all about using new mathematical problems, so looking at new mathematical problems that we think are hard for quantum computers to solve, as well as hard for classical computers to solve. And one of the areas that there's a lot of work on is around something called lattices. I'm not going to go into the maths of lattices because I'm not capable. But 3 of the current proposals that NIST are working through, which I'll talk about in a minute, for these algorithms are based on a mathematical problem of lattices. So you may hear quite a bit about that. So before we go further, just a quick mention, there's a QR code here. This is a course that myself and Alex actually, and some colleagues from my team put together. It's free. It is on the IBM website, but it's free, where you can learn a little bit about hash-based cryptography, symmetric key encryption, public key cryptography, and some of the aspects around quantum-safe cryptography. So feel free to take a snapshot of that and look at the slides later. Okay. Let's give a minute. Cool. Right, I'll move on. Standardization. So NIST, the American standards body, has been working with the community and issuing some competitions for people to come up with these new algorithms. It's been going on since around 2017, and we're now getting towards the tail end of that. In 2024, we expect those standards to be finalized. They're just gone through the last draft process. There's a big meeting coming up soon. And this should give us the final list of algorithms and the final kind of like parameters, the exact way in which these algorithms are used. These are the ones that currently feature, at least the top three, something called Kyber, dilithium, and Sphinx. They're used for two different things. Think about kind of encryption for the first two, signatures for the rest. I won't talk too much about the details, but they've got a few variations, like different key lengths, for example, that are part of that. But the bottom point is actually really important, which is when you look at this quantum or post-quantum cryptography, quantum-safe cryptography, combine it with an existing scheme. So you might use normal RSA encryption, and then you combine that with these quantum-safe algorithms, because these haven't been tested out there for like 20 years, like some of these other algorithms have. And yet we know our existing algorithms are vulnerable. So basically, you'll encrypt twice. There are concerns, of course, about things like key sizes, memory sizes, processing time, all that kind of thing that we all have to work through as a community. A few things that are happening in this space. MITRE, that was mentioned earlier, is a US organization that works very closely with the government. They've issued there's a charter, which is all based around a coalition that was formed in September of last year. IBM, Microsoft, you can see the companies here. This is what they're aiming to do. I haven't seen much in the way of public information yet. One of my colleagues is actually working very closely with the MITRE board on this. I know they're working through some things, but they've not sort of published anything publicly, but expect to see more from them in the coming months and year. Another really important project, we think, because we work with them, is one called Open Quantum Safe. And this is where we get to the open source software. This is where we get to something you can actually take and you can actually use. This is the website. It's now part of the Linux Foundation. And the objective of this project is to build these they already have built these open source implementations of the algorithms. And actually, at this point, I'm going to hand over to my colleague Alex, who's been working very closely also with the Quantum Safe organization, to tell you a little bit more.
Yeah, so looking at that fourth bullet point down there, focus areas of work. Unlike some of the organizations we've talked about earlier in this talk, this is a dev team. These are people putting out code, libraries, applications. So their two focus areas of work is one thing called liboqs, which I'm going to discuss in detail in the next slide, which is a C library that actually gives you an API to get these algorithm implementations for those algorithms we saw earlier. And then the other thing they're doing is they're making lots of prototypes and extensions that allow people to actually use liboqs. So putting it in those applications and protocols. And I'll also give an example of that in a little bit. So first thing, liboqs. It's an open source C library. Again, they're all part of the Linux Foundation, so it's very easy to access and open source, properly governed. It's a standardized API for accessing these functions. So you don't have to think about, okay, what are these implementations? You as a user just need to know, I want an implementation of one of these quantum safe functions. Here's an API for getting it. Right out at the bat, it does all these NIST standards that we've already discussed earlier. And because they know not everybody likes coding in C, they immediately made wrappers for many other languages, including Python, Go, C++, and Rust. They have a bunch of others. Those are the ones that are being actively developed right now. A lot of their other wrappers, like for Java, they made a wrapper, said, hey, here's a prototype for a wrapper. If the Java community wants it, you can continue. Hasn't gotten much development since they made it. Whereas the Python Go and Rust communities have taken their wrappers and really ran with them. They're actively developing to the day. So that's kind of liboqs. I also have the GitHub up there. It's on GitHub. You can go look at it now. And then we're going to go into an example, which is OpenSSL. Because OpenSSL is the most commonly used implementation of TLS, and it's open source, this is where they started with their prototypes. The OpenSSL prototype in particular is not really a prototype anymore, to the point where OpenSSL itself uses their prototype as part of their CI. When they test this concept of providers, which was introduced in OpenSSL 3 as a way for third parties to implement algorithms and put them into OpenSSL, rather than having to go to OpenSSL and say, hey, look at these new algorithms I made, can I put them in OpenSSL? Now they say, hey, I made a provider that lets me plug these algorithms into OpenSSL in a safe, easy way. So they made an OpenSSL provider for liboqs called the OQS provider. And as I said before, the OQS provider is the provider they use when testing, does our provider framework work during their CI testings for OpenSSL? And using this provider and OpenSSL, you can enable other applications like Nginx, curl, and HAProxy to be quantum safe. And we give a little stack there on how the providers work. But yeah, the OpenSSL OQS provider is where most of my work has gone so far. And it's just a great basis for work in other areas. Wanted to plug my blog a little bit. This is a blog tutorial about the dev side. This walks you through how do I set this up? How do I set up the provider? How do I set up OpenSSL, liboqs, and actually use them in my application for developers, if you want to develop in that stack, if you want to use that stack. Again, this is on IBM's website, but it's free. And it's a basic walkthrough. Okay, cool. Not keep you guys too late. So yeah, so the Open Quantum Safe related activities that they're currently doing in Open Quantum Safe is all about supporting getting these algorithms in the hands of the people who need to use them, allowing people to use quantum safe algorithms in their code without having to think about how they're implemented and whether or not they've implemented them correctly. They recently joined the Linux Foundation, and we'll give you a hint, hint, wink, wink. Listen for an announcement later this afternoon.
Noon Pacific.
Yeah, yeah. There will be big announcements related to OQS later today, so listen to those.
We might have had some extra foils in here if the presentation had been later.
Yeah, we were like, oh, if only we were giving this tomorrow, we could be talking about this already. But yeah, there will be some announcements from the Linux Foundation around OQS later today. Hand it back to Nigel.
Yeah, and just quickly to go back to here as well, and one of the areas of work actually as well is that there are a number of these different implementations of these cryptographic algorithms, and one of the big discussions is, you know, around the needs in different places of these algorithms. You may need something that's a very efficient in terms of processing or very small in terms of memory usage, but also proof. Actually use tools to prove that the implementation is safe. That's an important part of cryptography as well. So there's new development work that I'm involved in as well to actually try and make that real and give us algorithms to use. So really the thing we want to leave you with is to think about this. Think that the data that you've got out there now, that is encrypted. It might be safe for now, but it may not be safe in a few years' time. We can't tell you when that will be, but what we can tell you is people could take that data that you've got now and look at it in future. So think, how important is it? Does that matter? You know, where should I actually start? I need to look at my high-value data. I need to try and prioritize. Look around at the different implementations and projects, and we've presented on sort of liboqs and what's going on at the Linux Foundation. There's a lot of big companies behind that. But there's also a lot of smaller projects. There's a lot of academic papers. There's work that Cloudflare, people like that, for example, are doing. So there is a lot out there. So I definitely encourage you to look into this area more, ask questions, come and talk to the people that are involved in this space, and try and figure out what it means for you maybe as a maintainer of an open source project, right? Are you using OpenSSL? Is it easy for people to configure these things? Can you test it? Have you somehow hidden that configuration? You need to expose something else that we can, like point to the provider. There's issues around like what happens if you're root with the configuration, and then you can't see the variable that tells you where to get the modules from. There's all kinds of subtleties like that. But think about what it means to allow people to use these algorithms. If you're a user, ask those questions, contribute to your communities, and experiment. And with that, I think we're also got about 2 minutes free for questions. These are our QR codes. Do feel free to get in touch with us if you have any follow-ups. We'll also stay outside after the talk.
Comment, 9 a.m. Eastern. But question for you. You'd mentioned with libOQS that you'd implemented, Kyber and the rest. Nigel, in your lead up, you'd advocated the use of hybrid scenarios where you'd, encrypt classically, and I forget the ordering, which is, what Google and Cloudflare, et cetera, are doing today. Does that hybrid wrapping also occur in libOQS, or do you have to go through 2 operations?
As far as I know, libOQS doesn't do it itself for you,
But does OpenSSL support as a cipher suite that you'd just be able to say, do the wrapping?
Off the top of my head, I cannot answer yes or no to that. I want to say it should, but I can't. I don't want to guarantee it.
I think it does, but I also can't 100% guarantee it. There is also a colleague of ours, Mariam. She's got a new blog which will be out very soon.
As soon as I review it.
As soon as
I get home
did
and
my
review
review
it.
on Sunday before the conference. Alex is still doing his review. That's another colleague of ours, and she's going to actually take you through using. She's doing HA proxy and show you a more sophisticated example of using these libraries. Again, written along the same style. But I do believe that makes use of hybrid in the configuration that she's put in place for OpenSSL.
Thank you.
Thank you. Very, very interesting. I have a question about some of these techniques are quite new, right? And you were saying that's why you need a hybrid approach, right? Because you're not quite sure of them. So that opens the possibility that in a few years' time, right, there is a massive risk, right? And if these techniques don't work or don't work well enough, so what are you aware is being done, particularly from maybe big organizations that have more risk, like you mentioned trade secrets, state secrets, and
well, one of the areas, for example, MITRE is looking at on this last bullet is ensuring crypto agility, and actually that is important in the industry. So that's being aware that over time your needs for encryption may change, and that's why it's actually really important to understand how you're using cryptography and what the value of the data is. That gets into the metadata discussion we had earlier. We talked about S-bombs. There's actually a proposal for something called C-bombs, which I think is currently still being discussed. There's a couple of tools starting to support it, which is a cryptographic bill of materials. It's trying to add that information about your use of cryptography. And so moving forward, if we can get that in place and we know where we're using that cryptography, it'll make our options to change what we use in future earlier. But we shouldn't treat anything here as final. Because all of these algorithms that we come up with, the quantum algorithms, to my understanding, there's no proof we know that they can't be cracked. It's just we don't believe they can be cracked at the moment. And that's where things like quantum safe versus post-quantum, quantum resistant, the terminology, quantum safe, don't interpret that as meaning it's going to be safe forever, because it's not. We have to be agile. Okay, with that...
Thanks, guys. That was interesting. I think you've just answered my question. I was going to say, what is the definition of quantum safe? Because there's more algorithms coming out, isn't it? Like isogenies and things now, and elliptic curves.
And there was one isogeny candidate, actually, that fell out of the NIST process because people did find a vulnerability in it. So, yes, it is a moving target. There's been quite a lot of review in terms of what we have as the finalists, and we expect that in the UK we'll adopt those, but it's not final.
For the 3 names, the naming by committee seems to be settling into post-quantum when talking about the subject material as a whole, and quantum resistant when talking about the algorithms in particular. quantum safe is more of a almost legacy term now that a lot of companies are still using because it's what we've been using before we realize PR-wise it's not exactly the correct name because there is no guarantee it's safe.
And the final thing to say is remind your colleagues that when we talk about post-quantum cryptography, this is not quantum computing. This is absolutely normal classical computing that we all do in all of our code. We just need to be aware of it and pay attention to it. And with that, we'll hang around for questions afterwards if you've got any, and enjoy the rest of the conference. Thank you.